All right, this is a video over some similar problems to the section 3.1, 3.2 homework. So looking at this first problem, let's read what it says. It says, if the sample space S is an infinite set, does this necessarily imply that any random variable X, so how we define our random variable that we're looking at, that's defined from that infinite set will have an infinite set of possible values? The answer to this is no. And I'll give you an example in the follow-up of a situation where the sample space is infinite, but we can come up with an X, our random variable, that is not. So if you look, it's this last choice right here. It says the random variable X could have a finite number of possible values. For example, suppose a coin is tossed repeatedly until a head occurs. So that sample space right there is infinite because we don't know, we're not guaranteed that you'll get a heads. I mean, we think in theory, yes, you should get a heads, but technically it is possible we could just get tails, 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 tails. So that's a possibility of an infinite sample space there. Let X be 1 if the experiment terminates with at most 5 tosses and 0 otherwise. So they've defined the random variable so that you're either going to give it one of two possible outcomes. You're either going to report the answer as a 1 or as a 0. And that 1 is only reported if the experiment terminates with at most 5 tosses. So anything else into the infinite beyond 5 is always going to be reported as a 0. So this is an example of setting that random variable in a way that it is finite number of possible values. Okay. And then let's look at our second one. It says the number of pumps in use at a 6 pump station and a 4 pump station. So we have two different stations, one with 6, one with 4 pumps, will be determined. So we're looking at both of these. So imagine these two gas stations are across the street from each other. One's got 6 pumps, one's got 4 pumps, and we're just counting and looking and seeing if they have pumps in use, okay, at both, and we're looking at that at the same time. So give the possible values for each of the following random variables. We're going to call T, the random variable T, the total number of pumps in use. So again, you can kind of think about this as counting. So we could have 0 of them in use. You could have 1 pump, and it doesn't matter which station it's at, but we could have just 1. So imagine looking between the two stations, only one's being used. 2, 3. The maximum number we could have in use would be if each gas station had all of their pumps in use at the same time. So we would have the possibility that that would be 10 pumps running all at the same time, because 6 plus 4. Okay. Now, this next one's a little different way of defining that random variable. They're going to call this one X, and it says the difference between the number in use at stations 1 and 2. Okay, so station 1 had 6 pumps. So imagine that this one is at full running capacity, but the one across the street is not. So we could do 6 minus 0. We could have 6 minus 1. So again, I'm just kind of going through the choices of just if all 6 are running at the first station. 6 minus 2, 6 minus 3, 6 minus 4. Okay. You could then have just 5 pumps in use at the first one, minus 0, minus 1, all the way down to 5 minus 4. And then we would also get down to 0 pumps of use in this one. We would have minus 1, minus 2, minus 3, minus 4. So essentially, we're going to get all the integers between this first subtraction up to this last one. So this is 6. We have 5, 4, all the way down. We're going to have -1, -2, -3, -4. So every integer from -4 to 6. Typically, when you write a set, you write your list from least to greatest. It's not required, but it's just the kind of standard protocol. So that's -3, -4, -3, -2, -1. You could get 0 if you had 4 minus 4. 1, 2, 3, 4, 5, and 6. So that's all the possibilities of having a certain number of pumps running at station 1 minus the number of pumps running at station 2. Okay, and then U is going to be the maximum number of pumps in use at either station. So essentially, since they said either station, we're kind of unioning this. So if you look at the maximum number of pumps in use at station 1, you could have anything from 0 to 6, essentially, because this depends on what's the max number in use at that moment. Where you could have 0 to 4 for this one. So if you union those together, you have that overlap that's not just, we just don't double count it. So it's essentially anything from 0 to 6. And that encompasses both possibilities. since they said either. That's an or. Okay, and then Z is the number of stations having exactly 2 pumps in use. Okay, so you could have that happening. So if we pause for a minute and we look at the 2 stations, they could both not have exactly 2. So that would be 0 stations having exactly 2 at that moment. You could look in one side could have 2 running and the other could have 3. So we'd have 1 station with exactly 2. And the best we can do is 2 because that's the number of stations we have. So the best we can do is that we look and both stations at the same time have exactly 2 pumps in use. So that's going to be our sets for each of these random variables. Okay. All right, let's look at this next one. It says a contractor is required by a county planning department to submit 1, 2, 3, 4, 5, or 6 forms, depending on the nature of a project in applying for a building permit. Let Y equal the number of forms required of the next applicant. The probability that Y forms are required is known to be proportional to Y. That means that P of Y equals KY for Ys of 1 through 6, okay? Then our value, what is the value of K? Now they said hint, and this is just a probability fact. The probability of each individual single event from 1 to 6, because remember it could be 1 all the way up to 6 forms, all of those individual probabilities together should add to 1. So since this is KY, that's what that represents, we're essentially plugging in for the Ys, and we're still going to have that constant K. So if you plug in 1 for Y, you're just going to get 1K. And this is summation, so we add these together. If we plug in 2 for Y, we'll get a 2K. If we plug in 3 for Y, we'll get 3K. If we plug in 4 for Y, we get 4K. I'm going to erase that plus. It looks a little funny. Plus 4K. If we plug in 5, we'll get 5K. And we stop at 6K because that's the top of our summation. And remember, we said that this summation, where P of Y is going from 1 to 6 for Y, where we also know that P of Y is KY, where Y is getting substituted each time. That should equal to the probability that it's a total sample space, and so it's 1. Now, if we add all these together, that'd be 3, 6, 10, 15, 21, K equal to 1. So we can solve for the value of K by dividing. So it's 1 over 21. So there's that. Now, the next part is what is the probability that at most 4 forms are required? So this is going to be the probability that we have our Y being less than or equal to 4. So that's going to be each value. So you can essentially think of this, they're all equally likely because they all have that probability of 1/21st, essentially. So we're going to take each outcomes, so this would be from 1 to 4 forms, and we're going to times it by its probability, okay? So that's going to be 1 times 1 over 21 plus 2 times 1 over 21 plus 3 times 1 over 21 plus 4, because we are equal to 4 times 1 over 21. Now that's going to be 1, 2, that'd be 3, 6, 10. So this is 10 over 21. So that's the probability that at most 4 forms are required, okay? And that's because remember our Y is our values 1, 2, 3, 4, 5, or 1, 2, 3, 4 in this case. And the K we found to make up this probability equation they gave us, that was that 1 over 21. So we just had to add each of the scenarios from 1 to 4 together, okay? Now, what is the probability that between 3 and 5 forms inclusive? That means we include 3 and 5 are required. Okay, so same idea, probability of 3Y to 5. Sorry, I wanted to write 6. That's going to be, again, the same situation. So this is 3 times the probability that we came up for the K part, which is 1 over 21, plus this would be 4, 1/21, plus 5, 1 over 21 times that. Okay, so that's 7, 12. That'd be 12 over 21. Those are both divisible by 3, so that's going to reduce down to 4/7. So 4 out of 7 for this one. And then could P of Y equals Y squared over 86 for Y's 1 through 6 be a PMF of Y? Remember, that's probability mass function of Y. Now, here's the situation with this. We have to check this to see if it equals 1. So we have to do the summation that they've described. And if it doesn't equal 1, like this is supposed to equal 1, remember that was our hint, then we cannot say that that's a valid PMF. Okay, so we're going to write this one out. So this would be y equals 1 to 6. We have y squared over 86. So 1 squared is 1 over 86. 2 squared would be 4 over 86. 3 squared would be 9 over 86. 4 squared would be 16 over 86. 5 squared would be 25 over 86. Oops, we got one more to do. We got to go to 6. And then 6 squared would be 36 over 86. So we're going to, all of them have the same denominator. We're just going to add up those numerators. I might use my calculator for that one. Mental math only gets you so far sometimes. So that is 1 plus 4 plus 9 plus 16 plus 25 plus 36. That is 91 over 86. That does not equal 1. That's more than 1. And again, it has to equal exactly 1. So this would be no. There's a drop-down menu here, I believe, that just says yes or no. And the reason is that our probability is equal to something other than 1. It's equal to 91 over 86, which is not 1, which means it is not a probability mass function for our situation. Okay. All right, let's move on to number 4. Okay, so I might have to draw the sample space for this one because sometimes that's helpful when you're coming up with the probabilities. So it says 2 fair die, 6-sided dice are tossed independently. Let M equal the maximum of the 2 tosses. So if you get a 1 and then a 5, you're going to equal that to a 5. If you get a 3 and a 3, it's a 3 because the max is the same number. So it's just 3. So let's write out the possibilities. And I'm going to actually make a list over here, and then we will look at what is their maximum in each one. So I have 1, 1. That's a toss you could get with 2 dice. We could get 1, 2. We could get 1, 3. We could get 1, 4, 1, 5, and 1, 6. Okay. We could start with a 2. That would be 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. This is probably the worst part is listing out the set. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. I'm running out of room, so that's a 6. And then we'll slide this over 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Then we have 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. And then the last row is 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So that's 36 total outcomes of rolling 2 dice that are independent of each other. You just write down what you could have gotten for the number of dots on each side, or the number if it has numbers on it. So this is a cool thing because we're looking for max values. So the max values can only be things that are a side. So it has to be either a 1, a 2, a 3, a 4, a 5, or a 6. We're questioning what's the frequency so we can get the probabilities. So if you look at this first one, it's the only one that's going to come out as a 1 because it's the only time we have 2 1s. So there's only going to be one case where we have a 1 as the max value. The next thing is it's really interesting to note, and I'm going to change my color real quick. Let's do light pink. The max ones with a 2 are kind of in a little like L shape, a backwards L around that one. So a 2, 1, a 2, 2, and a 1, 2 are the only times 2 is the maximum number. So notice that's 3. And then we can kind of keep going with this. If you look at the little, it's almost like a backwards L. 3, 1, 3, 2, 3, 3, 2, 3, and 1, 3. Those are all the cases where 3 is the largest value. So that is 1, 2, 3, 4, 5. And if you keep going with this, there'd be for the fours, again, it's like almost like like I said, a backwards L. You'd have 1, 2, 3, 4, 5, or sorry, I counted the 4, 5. 1, 2, 3, 4, 5, 6, 7. My row's got a little off. For the fives, we'd have 1, 2, 3, 4, all the way over to 5, 5. That's 5, 6, 7, 8, 9. And then for the sixes, you have this whole like ending row and column. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that helps us if we notice that they're kind of, if you put them in order like this, they're going to line up kind of in these little L shapes where the max number of the reporting value we can see it's all kind of grouped together. Okay, so now we're going to turn these into probabilities. We said this was total outcomes of 36. So everything we divide is by 36. So for max value of 1, it's a 1 out of a 36. We get a 3 out of 36. I'm going to write it below that for this one, but we want to reduce that. So that'd be 112. We get a 5 out of 36, which does not reduce for 3. For 4, we had 7 out of 36, which does not reduce. 7 out of 36. For 5, we have 9 out of 36, so that is going to reduce. That would be 1/4. And then for 6, we have 11 out of 36. Okay. Now I left them in their 36s because when we make the CDF, which is called cumulative distribution function, we're adding the probabilities as we go. So essentially what we're saying here is before we ever got this first outcome, the probability of us before we reach the first possible random variable value is always 0. Now, when they say less than or equal, m is greater than or equal to 1, but less than 2, they're saying we've only encountered this first probability. So that's 1/36. When we get to this one right here, this is from 1 to 2. See, now we're equal to 2, but not quite 3. So we are adding our cumulative probabilities together. So that's 1 plus 3. That would be 4 out of 36. You can put 36 here too. So that's going to reduce to 1/9 for this one. 3 to 4, we're adding now these three, the first three together. So we're equal to 3. So that's 4, 9 out of 36. So that's going to reduce down to 1/4. Once we've added all the way up to the 4, so we have the 1 plus 3 is 4, plus 5 is 9, plus 7 more is 16. So 16 out of 36, I'll probably write that one down. So 16 out of 36, divide them both by 4, that's going to be 4/9. So we were at 16 out of 36. If we add the 9 out of 36 to that, we're going to be at 25 out of 36. So that's not going to reduce. So we're just going to write 25 out of 36. And then for the last one, we will add 25 plus 11, which is 36. So once you've gotten to, now we're equal to 6 or bigger, which means because it's cumulative, it's going on forever. Even though that's outside of that, our probability stays at 1. We've maxed out at that 1 probability. Okay, so that's our cumulative distribution function, or you can just say CDF of M. Okay, now we want to pick a graph. So key thing is you should, anytime it's cumulative that you're graphing, which is what we're doing here, the CDF, you should see it starting low and going high. It should never come back. It's always growing in probability until it reaches 1. So right now that already throws out the first choice here and the second choice, or the first choice on the bottom one. Also, this one's thrown out because it's decreasing. So as we go, the only one that even makes sense without me checking even all the decimals is this picture right here. So I'm going to go ahead and mark it. But let's kind of double check. So we're at 0 up until we get to 1. And notice they do not include the endpoint. That's why there's no dot there. We're including the endpoints on the left-hand side. Notice that. So we go from here. This is about 1 out of 36. You could turn that into a decimal if you need and see that it's just barely above 0. We're at 1/9. We're at 1/4 because now we're at about 0.25, which is 0.3 would be kind of middle. So that'd be halfway between there. 4/9. 25 over 36. If you turn these into decimals, you can kind of match them up. And then forever, once we get to this point at 6, it's 1 from that point on. Okay, so that's the correct picture for that one. All right, and then that leaves us with our last problem for this 3-1 to 3-2, just to help you kind of get an idea of what you're doing. This one's probably, it looks deceptively quick and easy, but you have to list out the sample space for this first part for A. There's actually 24 different possibilities, but they give you the first one, so you will not relist that one. You will list the other 23. So just be aware of that. They don't want you to list that, that first one again that they gave you, even though that's not the order I would have gotten them in. I'll show you how I work through this kind of just process of elimination. So it says, after all students have left the classroom, a statistics professor notices that 4 copies of the text were left under desk. At the beginning of the next lecture, the professor distributes the 4 books in a completely random fashion to each of 4 students, which we've labeled 1, 2, 3, and 4. Then they claim to have left their books. One possible outcome is that 1 receives 2 book, 2 receives 4's book, 3 receives his own book, or his or hers, and 4 receives 1. So notice this is saying the first position, they actually got number 2's book. In second position, that student got number 4's book. 3 is in the correct position because 3 got it in the 3rd spot. So that means this is the only student who got the correct book that belonged to them. And then the 4th student got number 1's book. Okay. So to set up this list, I kind of went through and started with book 1, and then I started with number 2. So I said, okay, what if numbers 1 and 2 both got their correct books? Well, 3 and 4 could have also, or, and I'm just going to write these side by side, it could have stayed 1 and 2, but 4 and 3 could have been switched. Okay, so 3 got 4's book and 4 got 3's book. Now, that's all the possibilities where 1 and 2 are correct, but 3 and 4 are not. Or, well, 1 they are and 1 they're not. Then I would do, what if 1 got its book correct? 3 is the next student. So again, incorrect setup for that person, but we're following this as in a sequence of kind of to eliminate all the possibilities. So if we've got 1 and 3 fixed in the first 2 spots, you could have either had 2, 4, or you could have had 4, 2. Then we'd have 1 fixed with 4. So notice I'm always fixing the number 1, and then my second position I'm fixing, and then I'm just flip-flopping the last 2. That's going to help us with process elimination to get all the listings. So this could have either been, sorry, let me start with the correct numerical order for numbers. That way I don't get off my pattern. This one would have been 2, then 3, because we already used 1 and 4, or we could have had 3 and 2. Then we now are going to start with fixing 2. Now, again, that's not the correct book for that person, but we're just fixing them so we can come up with the combinations. So it could have been 2 and 1, followed by 3, 4, or 4, 3. Then we could have had 2 fixed with 3, and that would be either 1 or 4, or 4 and 1. 2 could be fixed with 4 up front, so that would either be 1 and 3 left over, or 3 and 1. Just trying to go through all those possible combinations. And I'm going to try to just keep going down vertically with this. Then we could have, okay, so I did all the combinations with 2 fixed with the other character books, essentially the books, 1, 3, and 4. So now we've got 3 fixed with 1. We're going to have 2 scenarios for that. We'll have 3 fixed with 2. And then 3 fixed with 4. So let's fill in these. So if we've already used 3 and 1, it could be 2, 4, or 4, 2. This one could be 1, 4, or 4, 1. Because again, there's only one book that belonged to each student. So that's why we're not repeating any numbers in the sets. 3, 4 could be 1, 2, or 2, 1. And then now I'm going to do the 4 first. So this is if first person got number 4's book. So 4, 1, 4 fixed with 1, 4 fixed with 2, 4 fixed with 2, 4 fixed with 3. And we're going to double check that this is actually a total of 24 possibilities once we get done. But remember, one of them you would not type into the list because it's already been used in the original explanation. So this could be 2, 3, or 3, 2. This could be 1, 3, or 3, 1. And this one could be 1, 2, or 2, 1. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I got 2 columns, so that's 24. Note that you do not want to, in your typed up part, we had 2, 4, 3, 1. So don't list, if you had something like this where it says list the other 23 possible outcomes, if they've already given you one, don't relist that or it'll mark it wrong, even though you typed everything else in correctly. And that's just because of the way they worded the problem. But so let's talk about this. So the random variable is that X denotes the number of students who receive their own book. So in other words, the numbers are in the right place. So we're talking about, we're going to look through here and I'm going to use a highlighter. So I'm going to highlight, and this might make the ink look a little funny, but I'm going to highlight those who were, it was a set of 4 students and nobody got the correct book. So we can't use these first two because 1 and 2 got their correct book. And this one, everybody got the correct book. 1 still got the correct book, 1, 1, 1. So it has to be something where we didn't start with a 1. So this one, we got 2. So that's 1 got the wrong book, 2 got the wrong book, but 3 and 4 were fine. 2 we got the wrong book. Yeah, so if you look at this set right here, everyone got the wrong book. So 1 was supposed to be 2. So we had a 2 instead of a 1. We have the 1 instead of the 2. We have the 3 or the 4 instead of the 3 and the 3 instead of the 4. So everyone in this group got the wrong book. If we look at this next one after it, it is a similar problem right here. So nobody, oh, actually, no, sorry. 4 got the right book. So you have to look really carefully. This is where your eyes can kind of get against you because you're looking for that one situation where nobody got the right book. So let's see, 2, 3, 4, and 1. That would be one where, yeah, nobody got the correct book in this scenario. Let's see, 2, 4, 1, 3. Again, nobody got the correct book. Let's see, what else do we have? 2, 4, 3 is in the correct spot here, so we can't use that one. 3, 1, 2, 4 is in this correct spot. 4 is in the correct spot on this one. I might just do it by column. It might be easier. 3 is in the wrong spot. 4 is in the wrong spot. 1's in the wrong spot. 2 is in the wrong spot. So this is one that we have there. Let's see. Everybody's in the wrong spot on this one. Everybody's also in the wrong spot on this one. And let's see, 4, 3, 1, 2. So everybody's in the wrong spot on that one. Let's finish going down this column. Let's see, 3's in the right spot on this one that you didn't have to list, but it's still part of the probability. Let's see, none of these are in the correct spot. See, we've got 3, 2's in the correct spot on this one. Oh, so that makes me, I realize I just mistake. And this is why I do this in color, because it's easy to look at it and think it's right, and then it's not. This one that I highlighted, the 2 was in the correct spot. I was paying attention to the 4, 1, and 3, but the 2 is actually in the correct spot. So let's keep going. Like I said, this is why I draw it out. 2's in the correct spot on this one. 3's wrong, 4's wrong, 2's 1, and 1's wrong. So that one's wrong for all 4 positions. 3's in the correct spot, 3's in the correct spot. 4, 3, 2, 1 is in the incorrect spot. So let's just double check this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of the 24 that look to be in the nobody got the correct book. So all 4 students got the wrong books. Nobody got their own book, essentially. So let's put that underneath there. That's 9 out of 24. If we reduce that by 3, that's going to be 3/8. And that is the correct probability for that one. All right, so now we're looking for 1 student got the correct book. So at least that's not going to overlap with any of the ones we already did. So I'm going to use a new color. We're going to use green. It can't be the first one because everybody got the right book. And 1 and 2 got the right book. 1 got the right book. 4 got the right book. So that's not just 1 student. Let's just do column again. That'll be easier. 1 got the right book. 4 did not. 2's in the wrong place and 3's in the wrong place. So this one's one where only 1 person got the correct book. For this one, 3 and 4 both got the correct book. For this one, 4 is the only one that got the correct book. So that one's just 1 correct student. For this one, only 1 student got the correct book. That was 4 again. For this one, it can't be highlighted because 2 and 4 both got the correct book. For this one, we have 2 got the correct book, but nobody else did, so that one works. Let's see, 1 and 2 both got the correct book, so that one's out. 1 got the correct book, but 3, 4, and 2 did not. On this one, 1 and 3 both got the correct book. On this one, we have 3 has the correct book, but nobody else does, so that one counts for that green group. 2 is the only one that got the correct book on this one. Let's see, 3 got the correct book and nobody else did. And then 2 got the correct book and 3 did, so we can't use that one. So this is 1, 2, 3, 4, 5, 6, 7, 8 out of 24. I always like to write the original kind of underneath my work, and that reduces to 1/3. Okay. Then we're looking for 2 people got the correct book. So this one takes a while, not because of the listing, but because you have to compare all of these scenarios. So we're looking for exactly 2 of the students received the correct book, but no one else did. So it won't be this first one because everybody got the correct book, but this one, these last 2 are switched, but the first 2 are correct. 1 and 4 got the correct book here. So that's correct on that one. Let's see. 4 and 3 both got the correct book. So that one's included in the exactly 2. 2 got the correct book and so did 4. And then 1 and 3 both got the correct book. And 2 and 3 got the correct book. So this is for the blue, it's 1, 2, 3, 4, 5, 6 of them. So that would be 6 out of 24, which is 1/4 if you reduce it. And now this one is the tricky part. This is actually 0 because if you have 3 of them correct, it forces you to have all 4 correct because the 4th position has to also then receive their own book. So there's only one person out of the 24, or one, I should say, set where we all got our correct books. Everybody got the book that they actually left. This is because if 3 are correct, so is the 4th. So that means that's not a possibility, since if you have these 3 correct, you also have the 4th one correct, which means that it's not possible to just get 3 correct. You'd have to get all 4 correct. All right, so that answers that one. And again, it's easy to make mistakes. It's why I like to write out my sets and actually then I highly recommend highlighters or pencils, colored pencils, whatever it takes to help you see what you're doing. But once you get it all done and you figure out what they're asking, it's just a counting game. So that is it for 3, 1, 2, 3, 2.